Okay, so eta beta pi. Oops, that's not what I want. This is what I want. Eta beta pi. So here I'll be talking about pi bonds. So, hybrid theory and valence bond theory and multiple bonds. Pi. We're talking about pi bonds. Okay, so every hybrid orbital has some s orbital in the mix. Okay. Remember that, oops, we're going over here. A hybrid orbital, to make that, we combine multiple orbitals. So this is how we get, according to hybrid orbital theory, this is how we get our more complicated geometries. So we have an s orbital plus or minus a p orbital, gets us these two hybrid orbitals, each one of which is sp. And then we can also get sp2, sp3, sp3d, sp3d2. These all have s character to them. So every hybrid orbital is somewhat s. It's a little bit s. It's s-ish. Okay? So hybrid orbitals are called sigma bonds. Or the bonds formed using hybrid orbitals are sigma bonds. We call them sigma because this is the Greek letter for s. Okay? Sigma. So the first bond between two atoms is always going to be a sigma bond. Okay? Everything else is going to be a pi bond. So the second bond, we call it a pi bond. The third bond, we call it a pi bond. That's because when we make them, we don't use hybrid orbitals. Okay? Instead, they are made using p orbitals or d orbitals. And because we prefer the p orbitals, we call them pi bonds, that being the Greek version of the letter p. The result is that the first bond, the one with the hybrid orbitals, the sigma bond, is significantly different from the pi bond, the second and third bonds that come later. Oops. So first up, a sigma bond, because it's formed using these hybrid orbitals, it is very directional, and it lies directly between the two atoms. Okay, so like say we're looking at ethane again. We looked at that at the toward the end of the video last time, talking about geometries, talking about hybrid orbital theory. Each of our carbons is going to be sp3 hybridized because they have 4 electron domains. And thus, when they form their bond, they do so by having overlap with these sp3 hybrid orbitals. Now, the way the orbitals work, this place where you get the crossover, that is the nucleus of the carbon atoms. Okay, so this bond, lies directly between the two nuclei. You don't get that with pi orbitals. Pi orbitals are off of that nucleus because they are formed using p orbitals. Just p orbitals, and because of the way hybrids are formed. Or not just p orbitals, they can be formed using d orbitals. But the thing is, in order to get these orbitals with their great directionality that gives us the geometries that we're looking for, we have to use the p and d orbitals that have the directionality we want. They're pointing in the directions we want. So the p and d orbitals that'll be left over will necessarily not be pointing in the directions we want. Okay. So, like if you're looking at this guy, if we're making a linear molecule, say we're just trying to combine the two atoms to make oxygen, right? In order to form that first bond, oops, you can't see it very well because of the lamp. That's the opposite of what I want. Okay, there we go. In order to form that first bond, we have to use the p orbital that's pointing directly between the two oxygens. Therefore, when we want to form the second bond, we no longer have that orbital to use. Okay, that orbital is no longer present. So we have to use a p orbital that is pointing 90 degrees away from where we want in order to form that pi bond. So all of our sigma bonds, okay, so all of our sigma bonds will lie directly on the line between the two atoms. And pi bonds will always be off of that line. Okay, they will not lie directly on the line between the nuclei. Instead, they will of necessity be either above and below or in front and behind. And notice I said above and below or in front and behind. That's because remember, when we use the p orbitals to make that second bond, well, the p orbitals have those dual lobes, so they will be above and below at the same time. Or we have the one that's pointing in the third direction, and thus it would be in front and behind. Either way, it's off by 90 degrees. So now let's start counting bonds. Sigma and pi bonds. So the first bond is always sigma. The second and third bonds are going to be pi. So let's start here in the upper right. We're looking at ethene or ethylene, marsh gas. Okay. The first bond between the two carbon atoms was a pi bond or a sigma bond. The second bond is a pi bond. So that means when you have a double bond, one is sigma and one is pi. If all you have is a single bond, it's just going to be sigma. Okay. So this ethylene molecule has one sigma, a second sigma, a third sigma, a fourth sigma, and then a fifth sigma. It has 5 sigma bonds in the entire molecule, and then it has a single pi bond all by itself. Okay? The double bond is a sigma and a pi bond. Coming over here, we have propene or propylene. Again, it has a double bond. So that double bond is a sigma bond and a pi bond, okay, together. The rest of these are all single bonds, so they're just sigma. So 1, 2, 3, 4, 5, 6, 7 sigma, and then one more sigma and one pi. Propylene has a total of 8 sigma bonds and 1 pi bond. They're very likely to ask you to count sigma and pi bonds and give you a picture of a molecule. That sort of question is perfect for a multiple choice test. So for a much simpler molecule here, we have hydrogen chloride. A single bond between them means 1 sigma, no pi. Here we have oxygen with a double bond, 1 sigma, 1 pi. And then we have nitrogen. A triple bond means 1 sigma and 2 pi bonds. So this is what they look like. Remember before I was talking about the axis, getting off of the angle. These are sigma bonds right here. Okay, I'm in the graphic in the lower left. Okay. The sigma bond is always nice and strong because it uses the orbitals that give you the best overlap. And that is to say, they're the orbitals that point along the axes. Okay, they point between the two atoms. So you get good overlap, and they're really strong. Pi bonds, they can't use those orbitals because they've already been used for the sigma. So they have to use orbitals that are off the axis. So these down here are pi bonds. Here we have 2 p orbitals that are trying to overlap by standing side by side. Here we have a p orbital and a d orbital that are trying to overlap side by side. And here we have 2 d orbitals overlapping side by side. So a pi bond, because it doesn't get that good overlap, it isn't as strong as a sigma bond. So you remember when I talked earlier about covalent bonds, when we were first starting chapter 4, I said that a double bond isn't twice as strong as a single bond. A triple bond isn't 3 times as strong. This is why. It's because the second bond and the third bond are pi bonds. They're made using these perpendicular orbitals, and thus they don't get that amount of overlap, and thus they aren't as strong as a sigma bond. So a sigma bond and a pi bond together are stronger than a sigma bond alone, but the pi bond isn't as strong as the sigma bond. So this here is ethylene, marsh gas. Like I said, we have 1, 2, 3, 4, 5 sigma bonds and a pi bond. So we're looking at ethylene lying on its side. Okay, this hydrogen is coming straight out toward us. This hydrogen is going back away from us, and the same is true for these two hydrogens. So this is so that we can see the pi bond, sort of straight on. It is both above and below the molecule at the same time, and the electron density of the pi bond is located up here, and it's located down here at the same time. Remember, like I said, electrons are weird. They can be in multiple locations at once. And in this case, they are above and below at the same time, whereas the sigma bond is located entirely directly between the two atoms. So, reiterating, less overlap means the bond isn't as strong. A double bond is stronger than a single bond, but it's not twice as strong. A triple bond is not 3 times as strong because you don't get that overlap. Here is a nice example of something really complicated. This is acetylene. Acetylene is C2H2. You might have heard of it as acetylene gas. The stuff they use for welding. It burns very, very hot. So here in the middle of these complicated structures, this is a carbon atom. This is a hydrogen atom. Here's another carbon atom. Here's another hydrogen atom. C2H2, acetylene, or ethine. The carbons are bound by a triple bond, okay? And they also have a single bond over to the hydrogen on the end. So each carbon is sp hybridized. So here's one hybrid orbital, here's the other hybrid orbital for that carbon. Here's this hybrid orbital, here's that hybrid orbital on this carbon. So that first bond gets a good amount of overlap because those hybrid orbitals are pointing directly toward one another. Likewise, the carbon-hydrogen bonds get good overlap because of that hybrid orbital pointing directly toward the hydrogen. The second and third bonds between the carbons, they don't get that good overlap because I wish they hadn't done the lobes this way, but here we have the lobe that is above and below. The red here is up, the blue here is down, and it's overlapping with the blue down and the red up of the p orbital on the other side. And then for the third bond, we have this red pointing forward, the blue pointing back, overlapping with the same guy on the other side, red pointing forward and blue pointing back. Thus, this has 1, 2, 3 sigma bonds and 1, 2 pi bonds. And this over here on the right is showing us the electron density of those bonds. So between carbon and hydrogen here on the left, we have good electron density between those two atoms. Between the two carbon atoms, we have great electron density between the two atoms. And then carbon-hydrogen on the right, great electron density. So the sigma bonds are nice and strong. Good overlap, lots of electrons really holding those guys together. But then we can see that it doesn't work nearly as well for the pi bonds. Okay, this is a good, just graphical representation of the fact that because these guys aren't pointing directly at each other, they don't really get that good overlap. I mean, they do share the electrons. You are getting that bond. These are things that happen, but just because they're not pointing toward each other, it's harder for them to get that overlap. It's harder for them to really get that good electron density. So I think this is just a good way of showing that it looks a little bit more strained to me. Not only that, this is also showing us that those bonds exist above and below at the same time, in front and in back at the same time. So this is above and below. This one is in front and behind, although it's mostly hidden. Now for something really complicated. This is allene, C3H4. So the way allene works, let me bring up the camera. We have two double bonds between the carbon atoms. Okay. So we have carbon bound to carbon, bound to carbon, and then we have hydrogen, 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 hydrogen. But there's a weird thing going on with the way this works. So this hydrogen on the left, it has 1, 2, 3 electron domains. It's sp2 hybridized. This carbon on the right is sp2 hybridized. This guy in the middle, though, he is sp hybridized. He only has 2 electron domains. Now, let's say that when we're looking at this in terms of axes, we have 3 dimensions, right? So x, y, and z. So when I'm talking about these p orbitals, I'm going to be using x for the line that runs down the length of the molecule. Z for things that run up and down on the page. Y is for things that go in and out of the page. So in order for this guy, this carbon, to hybridize sp and point in the correct direction, it's going to mix its s and its px. These two guys, in order for them to also form in the correct direction, it's going to mix x, s, it's going to mix px, and it's going to mix a third p orbital. But this is where the weirdness comes in. Because this carbon here is going to have to form a double bond on either side. It's going to be using one p orbital for the double bond on the left. It'll be using the other p orbital for the double bond on the right. So it has also available to it py to form a double bond, to form the second bond, I should say, pz to form the double bond on the other side. So it'll be using py for one side, pz for the other. So one of these guys will have to use py to form the double bond on the one side. The other guy will have to use its pz. So let's go ahead and say that it does pz on the left, py on the right. That determines what these two carbons on these two sides have available for hybridization. Okay. This carbon on the left is using py for the double bond. Therefore, it can only use pz for its hybridization. Whereas this guy's using pz for its double bond, so he has to use py for his hybridization. The result is that these two guys, although they have the same kind of hybridization, sp2, they're going to have different orientations in space. S, x, y, okay, px and py, means that this one is oriented in terms of its triangle. It forms that nice flat triangle, trigonal planar, is going to be in the xy plane. So it's going to be, sort of going in and out. This one, because he's using py to form the double bond, using pz for his hybridization, he's going to be in the xz plane. So his hydrogens are flat within the plane of the page. Okay. So that is going to result in an actual physical geometry that we can observe. Okay. I just want to stress that this is not just random crap we're talking about here. This is based on actually observing real molecules. This is where the theory comes from. This is what Alene ends up looking like. Oh, don't scratch your ear if it hurts, buddy. That's why he's wearing the cone of shame, my dog. So here we have the central carbon atom, sp hybridized. It uses a p orbital for the double bond over here on the left. It uses a different p orbital to form the double bond on the right. Our two carbon atoms on either end are sp2 hybridized, and yet they have to have this 90-degree twist. One of them lies in the xy plane, the other one lies in the xz plane. So this is what we actually see when we look at Alene. The two pi bonds are perpendicular to one another. One of them is above and below, the other one's in front and behind. And the result is that the hydrogen atoms are perpendicular to each other as well. These hydrogen atoms are going in and out of the screen, towards you and away from you. These two hydrogen atoms are lying directly in the screen. Okay, they're perfectly flat. Now, would they ask you about Alene on the test? I very much doubt it. I mean, this could be sort of a bonus question on a regular in-person sort of test where you have paper and they expect you to write short answers. For a multiple choice test, this would be a little bit much. But I do think that this is nice and instructive. If nothing else, it shows you that this does have real results. These orbitals really do exist. All right. So that is pi bonds. Okay, just a little bit of review. Hybrid orbitals are always going to be sigma bonds, okay, because they are always going to form sigma bonds because they have s character to them. They mix in those s orbitals. That's what we call them, sigma. The second and third bonds only have P or D, and therefore we call them pi bonds. So you can count the number of bonds, and you can know how many sigma and pi bonds there are in a molecule, and that has real physical consequences for your molecule. All right. Oh, of course, the pi bond is always going to lie off the axis, and it's going to be weaker than a sigma bond. The pi bond will always lie above and below, or in front and behind. Okay, that is what I want to discuss with this. We will come back in the next video to talk about extended geometries, and that will... You know what? I'm just going to keep on going because it's going to take us about 5 seconds. All right, extended geometries. They asked you to do this a little bit in lab. I want to go over it again here in this video. You can find the geometries and the hybridizations for larger molecules, not just single center molecules. So here we have a very complicated, not very, but fairly complicated organic molecule. Okay. We can find the individual geometries and hybridizations of every single carbon atom and this oxygen atom, just to keep on going, along this entire chain. Okay? It's not particularly difficult. If we were trying to find the geometry of the entire molecule, that would be an exercise in weirdness, because this is a big thing. Instead, we find the geometries of every individual center along the chain. Okay? So, instead of trying to do that on the screen, instead of just talking at you, I'm going to go ahead and recreate this molecule here on my paper. So, H3C, CO, O, C, H, double bond C, H, C, triple bond C, CH3. Okay, so there is our molecule. There's our compound. In order to find the individual geometries and hybridizations, I'm going to go ahead and throw hybridization in there just to give us a little bit of practice. First, we need to find the number of electron domains for each center. So carbon, carbon, oxygen, carbon, 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 carbon. Okay. Once we know the number of electron domains, we can get the electron domain geometry. In order to find the geometry within the molecule, though, to find the molecular geometry, we need to know the number of lone pairs. And once we have that, we can get the molecular geometry. Knowing the number of electron domains, though, will also allow us to get the hybridization. Okay, what sort of hybrid orbitals did that atom have to make in order to get those electron domains, in order to get its particular geometry? Okay, so note that electron domain geometry and hybridization are both just based on the number of electron domains. But in order to get molecular geometry, we also need the number of lone pairs. Okay. So, this first carbon, it looks around itself. It has how many electron domains? Well, it has a bond to this carbon and also to each of these 3 hydrogens. It has 0 lone pairs. So, 4 electron domains. This carbon, a single bond, and 2 double bonds, gives it 3 electron domains. This oxygen, single bond, lone pair, gives it 4 electron domains. Carbon, single bond, double bond, 3, single bond, double bond, 3, single bond, triple bond, 2, 2, and finally 4. So our electron domain geometry, okay, for organic molecules, it's fairly limited, but that's fine. We have tetrahedral We have trig planar, tetrahedral, trig planar, linear, linear, and tetrahedral. For the number of lone pairs, well, it's rather straightforward. 0, 0, 2, 0, 0, 0, 0, 0. So the molecular geometries for most of these are going to be exactly the same as the electron domain geometries. Carbon really doesn't like to have lone pairs. Thinking back to formal charges, carbon really is happiest when it has 4 total bonds, whether single bonds, triple bonds, whatever. So long as it has 4 bonds, that's when it's at its happiest. If it has lone pairs, it is a relatively unhappy atom. So just tetrahedral, trig planar, tetrahedral, trig planar, linear, linear, and tetrahedral. Oxygen is the only one that's different here. He has 2 lone pairs, therefore he has a bent geometry. Now, as for hybridization, finding hybridization is pretty straightforward. It's just based on the number of electron domains. You have as many hybrid orbitals as you do electron domains. So you just count. So in order to have 4 electron domains, you need 4 orbitals. So what that is, let me go ahead and match the colors. sp3. SPPP, 4 orbitals, 4 domains. For 3 electron domains, it's sp2, sp3, sp2, sp2. For 2 electron domains, just 2 orbitals, so sp, sp, and finally sp3. And note that in terms of pi and so on, having that 3 domains, 3 orbitals, we have a p orbital left over here for this double bond. Each of these guys leaves a p orbital unoccupied to make this double bond. And these 2 carbons, just having 2 electron domains, sp hybridized, each one of them leaves 2 p orbitals available for this triple bond. So when we count the number of bonds floating around in here, how many sigma and pi bonds do we have? Well, in terms of sigma, we have 1, 2, 3, 4, 5, 6, 7, 8. I can't forget the hydrogens. 9, 10, 11, 12, 13, 14, 15, 16. So we have, did I miss one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. So we have 16 sigma bonds in this molecule. And for for pi, we have 1, 2, 3, and 4. So we have 4 pi bonds in that molecule. All right, so that is a segment of the kind of information they could ask you about. They could also ask you about bond angles. Tetrahedral means 109.5. Trig planar means about 120. This double bond takes up more space, so it squishes these 2 bonds down together, making this less than 120. Fine. This bond angle, it's tetrahedral, so it's about 109.5, but those 2 lone pairs means squish, so it's less than 109.5, and so on. All right. So those are the things I'm covering tonight. With that, we are done. Tomorrow I will finish Chapter 5 talking about resonance bonds. You can't see that. Talking about resonance bonds and a little bit about molecular orbital theory. So I am done for the evening. I will see you around.